Hello, my name is Kameron Reiter, and over the past year, I've been using the Green Bank telescope to observe and analyze low surface brightness galaxies. Whew, what a mouthful. So before we begin, I'd like to begin some acknowledgments. In particular, I'd like to thank Valparaiso University. I'd like to thank the undergraduate Alfalfa team, as well as I'd like to thank the Valparaiso University Department of Astronomy and Physics and the Green Bank Telescope and this university. I just also have these references as well that I used throughout the year, and their work is vital to my work. So standing on the shoulders of giants, as it be. So low surface brightness galaxies. Basically what these things are is exactly what they sound like. They are galaxies that can range from being small sort of dwarf-like galaxies to being extremely large galaxies, larger than our Milky Way. But the caveat of that is that they have low brightness. They have few stars per pixels in there throughout them. So the stars, rather, are diffuse to some degree. There are less stars than a normal galaxy. On the extreme end of that are ultra-diffuse galaxies, which are very large. They're the largest of low surface brightness galaxies, and they have very, very diffuse stars. That being said, the gas is not necessarily diffuse. Some of these UDGs can be gas-rich, and as galaxies form and as stars can form with gas, typically if you have a gas-rich galaxy, you're going to form a lot of stars, but some of these are gas-rich and not forming stars. Basically, they're very interesting. They are weird to some degree, and we want to find out why. And one of the best ways is to just collect data on them and find distances and do all that sort of thing. So, firstly, I am borrowing data, I should say, from the Hyper Supreme Cam survey, which was an optical survey that found about 781 low surface brightness galaxies. Well, that's a lot. So unfortunately though, because it was measured optically, we can't get the distances. These were found by just aiming at, say, fuzzy things in the sky and taking data on them. So while we can find a lot of these things, we cannot determine the distances. So we need another way. And that way is using atomic hydrogen. And atomic hydrogen is, exactly what it is, a proton and an electron. And sometimes, occasionally, this atomic hydrogen will go through a spin-flip transition, in which the electron will spin-flip. And when this happens, a photon is emitted that has a wavelength of 21 centimeters. Well, what does that mean? So light, just coming from, say, the sun and the lights in this room, are around 600-ish nanometers. And these are the range of 21 centimeters. So visible light is very, very thin, very short wavelengths, and radio waves are very long wavelengths. So in order to measure this, in order to detect this, we have to use radio telescopes. And also, why is it important that we measure the distances? And that's because of redshift. Redshift is essentially the Doppler effect. So as the Doppler effect happens, say with sound, when something's moving faster or when something's moving far away from you, it sounds like the sound gets sort of stretched out. Funnily enough, the same thing happens with light. And when an object is moving away from us, say a galaxy is moving away from us because the universe is expanding, the wavelength will be stretched out. So this 21 centimeter length will be stretched out longer than 21 centimeters long. So what we can do is we can actually, from this, we can find the redshift by subtracting the rest wavelength from the observed wavelength and just divide by the rest wavelength, which is lambda in this case. And there are some key exceptions that where galaxies that are blue shifted, such as Andromeda, which is blue shifted, it's coming towards us. But for all of these sources that I looked at, all 52 sources in our catalog, all of them are significantly redshifted to some degree, some more than others. But so we used the Green Bank telescope in West Virginia to actually take this data. Why did we use the Green Bank telescope? Well, alternatively, there's also the Arecibo telescope down in Puerto Rico. Unfortunately, Arecibo is a massive dish just in the ground, and it can only observe about 15% of the sky. Green Bank telescope, however, can rotate and move and change angles, and it can observe upwards of 85% of the sky. So it has a much wider range and a much better, we can look at much more of the night sky that way. So we can get a lot more data that way. And this data that's taken, I analyzed it through the GBT IDL software that is native to GBT, and I ended up having to write some programs to get around some like radio interference and GPS and some sort of that. However, that was done, and I did get some impressive results. Real quick though, this is actually what the official GBT observation sort of interface looks like. On the right is the sky view of where we actually look at our sources and we localize them and we center on them. And then on the left-hand side, we actually take our data and we get some great numbers, and we can get some awesome stuff from that. So, my actual data. So, this spectra was Galaxies 766, and it's notable because it's one of our most brightest sources. Some of our sources have been on the scales of, as you can see, the y-axis is in flux density, or how bright the object is, how bright it appears. The baseline here being the like the night sky, the background noise, in essence. And on the x-axis is the recessional velocity, or say the recessional velocity, how the red shift, in for lack of a better explanation. And this peak right here can actually help us, if we know that exact velocity of where that peak is located, we can use Hubble's law in order to get the distance. Hubble's law is basically a measurement of the expanding universe, and we chose Hubble's law. We used the Hubble's value of 70 kilometers per second per megaparsec, which is standard. And from once we knew the recessional velocity and we knew Hubble's law, we could just divide that out and get our distance. Distance recorded in megaparsecs. So I mentioned the flux density a little bit as being the y-axis of how bright it is. It's literally just the amount of light through this given area, and that's actually noted here with this integral right here. So that flux, combined with the distance, can actually get us the H1 mass of the galaxy. And this is really interesting. So we actually got about 10 sources that we were able to get the distances. I analyzed 25 of them, but we got 10 distances. Some of them were maybes. And this is the wonderful plot that we came up with. So the blue dots are all of the previous work that was done by Haynes in 2011 and 2018 with multiple contributors. And the sort of current catalog that we have, these 10 points, are the red dots. And one thing that is notable about this, by the way, just to emphasize it, on the x-axis is our distance in megaparsecs, how far away the galaxy is away from us. And on the y-axis is the log of the H1 mass in terms of like solar masses. So we notice that a funny trend here is that the red dots are all sort of like lower. They're in the lower, they're not extreme, but they are in the lower band. But that is purposeful because we're trying to find galaxies that are sort of in this area, below this threshold. There's a bias for galaxies above this threshold, but we are specifically trying to use the GBT to find things below it. And so far, we seem to be right at that line for some of these, which is really quite exciting. And hopefully, as we get more data in the future and analyze more sources, we can maybe get some actual sources like really, not far below it, but in this range. So, actually determining if these things are UDGs. And the way we can determine if a low surface brightness galaxy is a UDG is we have to set some parameters on it. And in Leisman et al. 2018, he defined that in order to be a UDG, it has to have an effective radius of greater than 1.5 kiloparsecs and a surface brightness of larger than 24 magnitudes per arc second squared. I will explain that in a bit. Basically, we have the effective radius in arc seconds measured optically. Johnny Greco was able to get that for us. And so that doesn't really help us, though, when it comes to getting it in kiloparsecs. So we actually have to use this equation right here in order to convert into kiloparsecs. So it's a simple equation, but it works tried and true, I guess. And that is located on the y-axis. Secondly, on the x-axis is the actual surface brightness that we had with optical measurements from Johnny, because we located these things optically based on their brightness. And we were able to get the G band of that by getting the I band and subtracting out the G minus I. And this allowed us to just get the G band. And notice on the left-hand side, as these numbers increase, it gets fainter, just because it's the larger a magnitude is in the positive direction, the fainter the object is. So, back to this. 25 sources analyzed out of the 52. 10 of them are confirmed detections, and if we take a broad definition, which is located on the red line, there we go, on the red lines here, there are 1, 2, 3, 4, 5, 6. There are 6 UDGs that we can say, yes, these are what they are. However, if we take a stricter approach to it, of defined in Leisman et al. 2018, we find that there are only about 3 that are located here that are confirmed UDGs. So, in summary, we looked at 25 out of the 52. We got 10 detections that were guaranteed, obvious detections. There were some in there that were maybe detections. They were possible detections. They need to be looked at further. And the ones that we aren't sure whatsoever, we need to set upper limits to as well. We need to set upper limits and make sure that these things are actually able to be used and plotted. Also, there are some that are just completely unusable, and the data is, unfortunately, really, really bad. And that's going to need to looked at later as well. So in the future, I would hope to continue on this more and to finish this catalog, if not continue it, so that someone else may also pick it up as well as work on it. So, any questions? Settle up. I'm thirsty. Yes?
So when you were talking about the broad and strict definitions, what is that like? Like if you go by the strict one, I guess, what does that mean about the other ones? Are they technically like normal galaxies? Like,
No. So these are all low surface brightness galaxies.
Okay.
But if we want to find out if they're the extreme low surface brightness galaxies or ultra diffuse galaxies, then we need to set sort of boundaries, like limits on it, to make sure if they are or not. And if you make the parameters stricter, then you are eliminating candidates. And these parameters, precisely the strict ones, I mean, were in Leisman et al. 2017. And so we are still sort of like working on that, and we want to get more data points to see if we can actually, maybe there are more that lie up in here or in this area here. So
kind of like you need more data to know whether the broad or the strict definition is the one.
Yeah, more data points would be absolutely wonderful. And these points that lie outside of the barriers, we suspect are just normal low surface brightness galaxies and may not be UDGs at all.
Okay.
So,
Thank you.
yeah, thank you. Any other questions? Yes?
Can you go back to slide 10, I think it was?
Yes, this one.
So the blue dots there, they're just radio observations of galaxies in general.
Yes, yes,
Okay.
they are.
Okay. All right, that was clear. Okay, so
Yeah.
so the fact that your red dots are at the low end of hydrogen mass.
Yes. Yes, because that's actually where we were, purposely that's what we were trying to find. There is a bias. There is bias. Obviously, like, there's not just a hard cutoff line here, which means there's no galaxies here whatsoever. It's just that there is a strong bias and we can't find it, particularly through Arecibo. Wouldn't be able to detect those galaxies. But with GBT, we might be able to actually get below this limit and see more galaxies that are here instead. And we're actually approaching it with some of those dots, with some of the data points.
So, so the fact that this seems to curve down and have less hydrogen in closer galaxies is an artifact of detection thresholds, or is that?
Yes. Yeah, it is detection thresholds. Yes. So.
Other questions? Students?